Well, good afternoon, everyone, and thanks for joining us today. My name is Fatima Babayan, and I'm representing the IEEE Victorian APN MTT Joint Chapter here with Les in Anasta. So today we are going to have our first event in 2021, but we have planned to have some more events throughout the year. Our aim is to have at least one event per month, but we are open to more talks. And we are going to invite a few distinguished lecturers this year, as well as having some talks from experts in industry as well as academia. And also we have invited a few postgraduate students to share their experience as well as their research outcome with us. And also we will have some hands-on workshop and competition that probably will be ready next month for advertisement. And our request is that if you have any suggestion or you are interested on any specific type of event or any speaker that you would like us to invite them, please feel free to contact us. And you can find our contact detail from the chapter website. If there is no question, I would like to ask Les to continue, to start this session. Thank you.
Okay, thanks, Fatima. It's my pleasure to introduce our speaker today, Ann Nguyen, who tells me he prefers to be called Frankie. He's in the final stage of completing a PhD at La Trobe University, and his talk today is on a full duplex antenna for the 5.8 gigahertz ISM band. So in this presentation, he'll be discussing the design and implementation of a single layered slot antenna for in-band full duplex operation applications at 5.8 gigahertz without the use of a coupler. High port isolation is achieved in this in his talk by strong separation of the even mode and odd mode feeds. Microstrip coupled coplanar waveguide is used at the transmit port to excite a step slot antenna in the odd mode. On the opposite side, a microstrip T-junction power divider is employed at the receiver port to feed two offset fed step slot antennas in even mode. Port isolation is further improved by 30 dB by using a lump capacitor at the termination of the coplanar waveguide. And he'll also discuss equivalent circuit models which are used in the impedance optimization process. So some background on Frankie, originally from Hanoi in Vietnam. He received the BE degree in electronics and telecommunication engineering from Hanoi University of Science and Technology from 1998 to 2003. Then from 2006 to 2008, he joined the master's course on microwave and antenna at Korea Advanced Institution of Science and Technology. Then from 2012 to 2017, he joined Motorola Solutions as a senior engineer designing RF hardware for two-way radio communication, a walkie-talkie type product. He then joined the PhD program of RF IC and antenna at the Center of Technology and Fusion at La Trobe University from 2017 to now. In between, he worked as an R&D engineer at hardware companies, including Tosi Robotics and ATS. So we're looking forward to your talk, Frankie, and I'll hand over to you.
Yeah, thank you very much. Today I will talk about my high isolation slot antenna for full duplex system. And this is my antenna. First, I talk about motivation and research aim and my thesis and the contribution and the full duplex antenna and The final one is a conclusion. And my thesis divided by 3 sections. So the first, the motivation, including the miniaturization, I mean that's small size and high data rate and longer battery life or low cost for our app component at 5.8 gigahertz. So according to this motivation, so in order to achieve it, we divide into 3 research topics, including the high linear CMOS power amplifier, harmonic suppression antenna, and full duplex antenna. So basically, my thesis including three chapters, and in order to do so, I divide by the each research topic got the performance improvement. For example, the CMOS power amplifier. So I will improve the PNDB point and with very simple schematic. And so I will do I fabricate the high linear CMOS power amplifier to do this. And for the harmonic suppression antenna, I do with the narrowband application and the wideband application. With the wideband application, I have a paper, namely wideband triangle slot antenna with our band rejection. So this one was accepted in IEEE letter. And with this antenna, I can achieve the size reduction and strong reduction at the unwanted bandwidth, and especially the bandwidth of the antenna is increased. For the full duplex antenna, I achieved the size reduction and 50 dB isolation with the moderate band around 10%. So this paper was accepted in the IEEE China action of the antenna. And now I will talk about the full duplex antenna. So this is a concept of the full duplex. In-band full duplex. It means that in-band, it means that the receiver frequency and transmitter frequency will be the same. It different from the half duplex, mean that the half duplex, the receiver and the transmitter frequency is different. So that's why you can see here, compared to the time division duplex and frequency division duplex, the full duplex can double the wireless capacity. And it is a full duplex antenna in the I developed here. You can see here there are 2 ports, port 1 and port 2, and port 1 in the 2 port you can assign any receiver or transmitter in any of the 2 port, and it is on the ground, and the slot, it is a step slot on the ground, and you can see here the capacitor here is for the improves isolation up to 20 dB. So with the 2 port like this, with the configuration like this, I don't need a coupler for the, so it can reduce the size or can reduce the number of layers. So here's I talk about a little bit the theory on the coupler like waveguide. Here you can see the coupler like waveguides, and on the right hand is the matrix represent the principal working of the slotty CPW, and here you can see the A0 and AE. A0 is the incident wave of the odd mode, and AE is the incident wave of the even mode, and the B is the forward reflected waves. And here you can see here the slot A and slot B. So the slot T can use for transmitting both the even mode and odd mode. So in my antenna, in order to excite the slot T in the odd mode, I use the kind of microchip and couple with the CPW light here in, you can see here. And for the working principle of the couple CP couple microchip in odd mode, in the figure 8, you can see the red line and the blue line. the red line and the blue line here in the odd mode. So in the same direction, and you can see here is a electric field of the slot coupled to the microchip light. So the electric field of the red line and blue line are in the same direction, so it's changing each other. On the other way is even mode. Here in the figure B, you can see here that the electric field in the two slot are the opposite direction to the microchip line, so it cancel each other. It means that the microchip line cannot get any energy from the slot line and vice versa. So it means that with this kind of configuration in figure B, it only transmits the odd mode. So I can excite the odd mode using the microchip line excited to the CPW. And you can see here in my HFSS simulation at 5.8 gigahertz, you can see at the figure A is the odd mode. So you can see the zero number of electric field surface current here, a couple from the microchip light to the CPW light. And, sorry, so this something come out in the figure B. In the figure B here, you can see when the CPW port is excited in the even mode. So almost there's no surface current running on the microchip line. It means that there's no energy coupled from the CPW line to the microchip line. So due to the because you can see here the line is not symmetrically according the CPW. So there are some still energy leaking from the microchip line to the CPW light. You can see here. So you can see here is my antenna, and this is when the port 1 excited. So you see here when the port 1 excited, this is a surface current vector. When the port 1 is excited, so the antenna working in the odd mode, and you see here the port 2, there are almost no energy come to port 2. And here you can see the electric field. Electric field here from when the port 1 is excited, you can see the red color. So the energy come to port 2, we got a slightly very small energy. And similarity in the figure like this, when the port 2 is excited, you can see here there's almost no energy come to the port 2, port 1. So here is similar when the port 2 is excited. So the energy transfer to the port 1 is very limited. Here you can see the electric field here is very small. So here you can see the simulation. You can see the isolation between the two port 1 and port 2 is the dot line here. The dashed line here, you can see when the port 1 or port 2 excited, so the isolation around minus 30 dB isolation. However, minus 30 dB is not enough for the full duplex system, so we need to improve it. So in order to improve it, we put a capacitor in end of the CPW light. Here you can see here the position of the capacitor, and you can see here after putting the capacitor, the isolation in the solid line improved from 30 dB to more than 60 dB. And the principle is that the coupling factor, it can be equal to S21 and plus the S23 or S31 and plus gamma L, and gamma L is a reflect coefficient at the port 3. And here the port 1, here the port 2, and the port 3 can consider here is the port 3. So the gamma L can be used to cancel out the S21 to be equal to 0 here. So you make this part and this part is cancel each other. So So in order to implement the gamma L, we can put a capacitor, because the capacitor they got a lot of small step in commercially, and I didn't choose a resistor here, because the resistor when consume the energy, it means that some energy from port 1 and port 2 will consume will transform into heat by the resistor, so it reduce again. So I choose only the capacitor, and the inductor is not chosen here, because the inductor they got the value of the inductor is not have a smaller step, and the price higher than capacitor, so I choose the capacitor here. So here in the equivalent circuit and the design step of the antenna, because the antenna have a two port, so when you change one parameter, it will affect to one port, or it will affect to two port. So it very confused for the designer. So I develop a equivalent circuit here to help the designer to understand which parameter affect to the port 1, and which parameter is affect to the port 2, and which parameter affect to the two port. So here is the equivalent circuit in the odd mode, and here you can see here the slot antenna represented by the that slot here, and the CPW line is excited by the voltage source in this way, and it equivalent to the two parallel CPW line here. So you can see here is the microchip line excited the voltage source here for the two parallel line happen by the CPW light, and this is the slot antenna, and this is a equivalent circuit in the even mode. So here you can see that the CPW is happen like double the value, and at the end of the CPW lines. So why in the physical meaning, it means that the value of the CPW line is double, because the electric field in this exactly position is the same, because the same direction, so it double the strength of the electric field here. So that's why the value of the capacitor here is double. So you can see here the impedance of the CPW line is loaded into the slot antenna like this. So it from the equivalent circuit, you can see that some kind of parameter like H2M and H1 and H2 will affect the impedance at the port 1, while the step slot dimension, or the CPW dimension, or the CPW will affect the impedance of the port 2. So in the port 1, because the electric field in exactly this location is cancel each other, so it equal to 0. So the capacitor doesn't have any effect to the impedance of the port 1. So that's why it does not appear in the equivalent circuit of the port 1. So here in the design is my design guidelines. So first we can put the initial value. We can calculate the initial value to the around the halfway length to design the antenna first. So we design the stepway antenna first, and then we can change the rectangular slot to the step slot to make a wider bandwidth. And after that, we can put the quarter wave microchip at the two fitting. For example, here you can put the around quarter wave length, this one around quarter wave length, and the microchip line fitting here is also 1/4 wave length. So the quarter wave length is a transformer, impedance transformer, to transform the impedance of the slot line to the 50 ohm. So it's very easy, like only the quarter wave length microchip, or the halfway length slot antenna, And for the CPW, the initial value you can calculate from the impedance around 50 ohm. So the at the 5.8 gigahertz, the value of the capacitor is around 0.55 picofarad. So it's the initial value for you to optimization. And after do everything and put the CPW in, and we can achieve around isolation around 50 ohm. And then after that, we can fine tune, and we can do everything on the parameter to get the S21 below minus 60, and at that time we can finish the optimization. So and begin to fabricate. And you can see here these are my fabrication antenna here on the top view on the left hand and the bottom view on the right hand. So the antenna is very small, and you can see here very low profile, very simple antenna with only the capacitor I put here. And here is the S parameter performance. The dashed line is the simulation, and the solid line is the measurement results, and it's quite match each other for the two port. And the most important parameter here is the S21 and isolation around below minus 50 dB across the operating bandwidth in the shadow rectangular here. You can see like this. And this is for the radiation pattern of the port 1 and port 2, and both of them like omnidirectional for the port 1 and port 2 at 5.8. And it very much with the simulation. And for the gain across the bandwidth, so the gain around 5 dB or 6 dB height, and quite similar, around it different between two port only 1 dB. So this is my performance comparison between the recent antenna. So here you can see there are some reference antenna, like the antenna in number 4, they use only the CPW, and the isolation they get around 30 dB. And some antenna they use coupler, and they use the deflected ground structure, and they get minus 35. And some antenna is a coupler, so they can achieve 50 or 40 dB. But the disadvantage of the coupler, like I talked before, it increase the size. So you can see here the size of the coupler. One is a 4.5 wavelength. Or you must increase the number of the layer to have a coupler under the antenna, so you can get smaller size. And the antenna in 13, they use a decoupling method. It means that you put they got the two separated antenna, and they put some resonator in between the two antennas to reduce the mutual coupling between the antenna, and they can get around minus 30 dB isolation. However, it comes with the price of the size increase around 3 times of the wavelength. So and the final one, the 14 one, they use a reflective terminator, which is similar to our method, and they get only 40 dB isolation, and the size is still bigger than, because they use the three separate ports, so the size is bigger. The size is bigger than our antenna, the size around 1.7 wavelength unit. So our size is not, although it's not the smallest, but it kind of the only second, because the smallest one they must use two layers. So and compared to other like Mach gain, so we get around 6 dB gain. And the antenna here, they use the array antenna, so they can get around 12 dB. And this one, they can use two antenna separately, so they can get around 8 dB and the patch antenna. And the bandwidth around, our bandwidth around 5.8 percent, which average here. And I am the only one who work on, he designed the antenna, work on the 5.8 gigahertz, while most antenna focus on 2.4 gigahertz. So in conclusion, our antenna got the target isolation with which is 50 dB, and the second best side, but earlier simple single layer PCB, which can reduce the cost. So conclusion, here the compact antenna is proposed at the 5.8 gigahertz. So the antenna show a very high isolation with the moderate bandwidth, and while they maintain a small size and a low profile of the single PCB. So the antenna can be the suitable candidate for full duplex system, and especially here we develop an equivalent circuit model to easier to the impedance optimization process. So do you have any question?